we're going to be doing LLMs and whether or not they're good anomaly detectors. And if we find that they're not good anomaly detectors, then what are the alternatives? If my name does not already give it away, yes, I am the second French speaker. I don't have an accent this time. It does come out when I'm back home, though, so don't catch me when I come back from France. So this is me. I'm going to keep it super short. So I work at Theodore, whose offices we're in. I'm a tech lead and developer, and I also do some data engineering. So my little fun fact is I've lived in 6 countries and moved 8 times before I was 18. No, my parents are not diplomats. Just a question I always get. But yeah, spies I've also gotten. I had to convince some people they really weren't. So why data anomalies? So some of you might not know the stat, but actually in the US, the average company loses 12% of their annual revenue due to bad quality data. So why bad quality data, and why is that so important to your revenue? Well, data is used for important decision making. When your data quality is bad, it also affects trust with people within your company, trust with your users, trust with stakeholders, everything, and also security. So when you've got bad data quality, it can also mean that you're at risk, that you've got some security issue, there's things you might not be picking up, and lots of other reasons. So that's only kind of the top 3, but it's understandable that 12% average annual loss. So there's a long list of things that can be a cause of bad quality. This is non-exhaustive. So you have the classic missing data and incorrect data, but you can also have out-of-date data, things which are inconsistent in format and standard, which just means that it makes it a lot more difficult to then actually do any analysis on it, incompatible systems, and of course, data complexity. The more complex something is, the more difficult it is to interpret. Okay, so what can we actually do about it? This is quite funny because Soufflé was our first talk, and I think elementary we're going to be speaking about in the next talk, and so you can use both of them. So there are existing tools that already exist out there. They're great for data observability, so these can be used when you want to improve your data quality. You can also spice things up a little, and what I mean by that is how good is OpenAI? So we're going to cover 4 things. Why are we doing this? Why are we trying to throw OpenAI at anomaly detection? We're going to do a basic test of just running OpenAI as an anomaly detector. We'll then look at some prompt engineering, and finally we're going to look at the effects of data type on how good it is at picking up anomalies. So why are we doing this? There's 2 potential reasons. The first one is flexibility. When you get data coming in, your data, it could be structured, it could be unstructured, it could be semi-structured. There's so many possibilities of how your data could be nowadays. Like you can have audio, video. It's not just limited to numerical and textual. So having an anomaly detector which is flexible could give you that advantage. But the second reason, and probably the most important, is curiosity. We're throwing OpenAI everything. Let's throw it up one more thing and see what happens. So our basic test looks a bit like this. I've tried to keep the code to a minimum for these slides. I'll show you, I've written 2 articles with the whole code that I used here, so feel free to check those out. I'll put a link to it afterwards. But this is what it looks like when you're kind of calling OpenAI. In the system, I'm telling it that it's a data analyst and I want it to spot any anomalies. I've kind of given it very limited information there. And then I'm giving it some data input and I want it to figure out something's wrong. Spoilers, it's that -1 cost over there. Later, we'll be using more complex data. So this is literally just something I got off Kaggle. It's electricity consumption in the UK, and that's what I'm using for the remaining of the tests. Don't worry, you don't need to know what all of these numbers are. There's just lots of numbers. So can any of you guess what happened in the basic test when I ran that anomaly detector? Do you think it did well or terribly? Yeah. It was absolutely terrible. And most of the time, it found absolutely no anomaly at all. It even got confused with that -1. The rest of the times I ran it, sometimes it had exceptions. GPT-4 performs better than GPT 3.5, kind of expected. The more anomalies it had, the more difficult it was to find. But one thing that was kind of surprising is the number of lines I gave it didn't make it any better or worse. It was more to do with the number of anomalies it had. So on average, with 2 anomalies and 20 lines of data, GPT-4 had a 32% detection rate of intended anomalies. So not terrible, but also not amazing. You can't use that in an automated system. It's just not reliable enough. Okay, so step one, basic test, 32%. Can we get it to do any better? So I went to do some prompt engineering and found 3 techniques. If any of you are not familiar with prompt engineering, there are lots and lots of techniques that you can use to improve OpenAI to get it to give you results that are more similar to what you want. So the first one is chain of thought. Chain of thought, when I first came across this, I was really surprised how such a small thing can have such a big impact on how your model does. And all it is chain of thought is telling it to, let's think step by step. That simple. You're telling it to break down its thought process, make things simpler for it to then process your response and say something out of it. So what does this actually look like concretely? There's a lot of text here. You don't have to read it all. The most important thing is this part here where it says, let's think step by step. So by making the model slow down its thinking, you're getting it to think twice. Yeah, think twice before it actually gives you a response. And that gives it a little boost. So instead of 32%, it actually pushed it up by 8% of detection of intended anomalies. So not too bad, doing pretty good, but not yet good enough. Second thing I tried out is few-shot learning. So few-shot is when you give the model a few question and answer pairs. So you're telling it, this is an input a user is giving you, this is what I'm expecting you to return. So here's an example of what that looks like. I have some CSV files at the top, one with an example of bad data, one with an example where there's no anomalies at all. And here's what I'm kind of expecting. The first time around, I'm expecting it to pick up 2 anomalies, and the next time I'm expecting it to find nothing at all. So what you're then doing is kind of putting words in the model's mouth where you're saying, okay, the user gives you this, you should be saying this. The user gives you this, you should be saying this. And then finally, the user actually asks the intended question of, can you pick up anomalies in this data? So you're kind of doing a mini training of the model by giving it a few of those back and forths. And that does exceedingly well. So you go up by 24% in the detection of intended anomalies. This is not compared to when we were using chain of thought. This is compared to the baseline. You have plus 24% in the detection of intended anomalies. So that's pretty good, but still curious. Let's try out one last prompt engineering technique. And that is self-reflection and multi-step. So in self-reflection and multi-step, instead of using a single model, we're going to break it down into 3 parts. In the first part, you're telling it, here's some CSV, find me some anomalies. The model gives you the anomalies it thinks, what it thinks are anomalies. The second time around, all you're really saying is, are you sure? Take your time. That's all the prompt is. It's literally telling it to rethink its answer and challenging it so that it has the opportunity to change. And then again, output with the anomalies. The last step is kind of to help you if you want to make it an automatic process, putting it in JSON. Because if you put it in JSON, it's much more practical for the next step in your analysis. So just giving it a schema and told it to convert it to that. For this one, you don't need something as powerful as GPT-4. GPT 3.5 is more than enough because all it's doing is converting your answer into a JSON. And so by breaking things down, by giving the model less to think about, compared to the baseline, you actually push up the percentage of intended anomalies detected by 28% as well. So it's very similar to what we saw with the few-shot learning. Unfortunately, when you put all 3 of these together, they don't all add up. That would be way too nice, but you still go up to 68%. So it went from 32% to 68% with some prompt engineering. I haven't tried every single one of the prompt engineering techniques, so there might be some others that push it up even more, but this is kind of just to give us a feel of how OpenAI reacts. Okay, 32 to 68, pretty good. Now, what about the data types? So what I mean by data types is there's a lot of different forms of data you can have out there. Like I mentioned, you can get speech, you can get images, you can get text, and you can get numerical. So I focused on text and numerical because those are quite big fields of data types, and why not test it against each other? So it wouldn't be far to say that almost, I don't want to say this without any stats to back it, but don't take completely my word for it. Numerical data probably makes up most of the data around the world at the moment, because we get it from sensors, we get it from medical devices, we get it from financial stats. There's a lot of things which are numerics. But we tried numerics and we got up to 68% detection of intended anomalies. So what if we tried some text instead? So for the text, I used movie reviews. I won't necessarily show it to you up here, but it's just been movie reviews. And this is what we see. So that's the statistics we had. I purposefully didn't really mention how GPT 3.5 kind of improved over time, mostly because it didn't improve over time. It was very stubborn with the prompt engineering and decided not to really do well. So it had about 16% detection of internal anomalies, and GPT-4 had 68%. Now, as soon as you move away from numerical data and you go into textual data, it does way, way better. So GPT 3.5 goes to 78%, and GPT-4 goes to nearly 100% of accuracy, which is absolutely amazing. But then when you think about what OpenAI is, it's a large language model. It hasn't been trained to do maths. OpenAI is notoriously bad at maths, and I guess we proved it once again that it is very bad at maths. But great, okay. We're at, this hides it, but we're at 100%. We're at 100%. That's amazing. Yay, we can stop here, right? Not really. We just proved that with text, you can reach 100%. But like I said, a lot of data is numerics. You can't just kind of abandon that, put that to the side. We probably should address it. Okay, so OpenAI doesn't quite work with numerical data. So what does? One option is trying to use BigQuery. So BigQuery actually has an inbuilt anomaly detector. It's not very known. It took me a while to find it. But there's basically just 3 clear steps that you have to go through. The first thing is you have to choose a model that fits your data. In our case, it was energy generation, so it's a time series. So I used their ARIMA Plus model. The second step is you create a model for each data column. So kind of a little bit annoyingly, you can't do all your data columns in one shot. You do actually have to train individual models for each of the data columns. And then finally, you run the anomaly detector for each data column. I'm not going to bore you with a huge text of code. So once again, I'll show you where to find it later. But this is the most important piece of code. It's quite simple, which is really nice. Disclaimer, the code that has to go around that is probably 100 times longer, so not that easy. But this is what it looks like. So you do ml.detect anomalies, you give it the model that you just trained, and you're giving it this anomaly probability threshold. What that means is that what BigQuery will be doing under the hood is it's going to give you a probability of something being an anomaly, and you have to tell it, okay, at this threshold, classify everything above it as an anomaly and everything below it as not an anomaly. So like you can see here, we have it at 0.95. So this is going to be a bit important for the rest. Okay, great. It is actually really good. It detected 100% of intended anomalies. But it's got a different problem. Finds all the anomalies, but it gives you a whole bunch of false positives. So you actually get, out of 28 lines of data and 5 intended anomalies, it gives you 21 false positives. Okay, so it found all the intended ones. That's great. That means they're not going to kind of slip through the pipeline. We're going to pick up on that bad data, but this is going to get quite annoying. It's going to trigger lots of alerts. It's going to tell you that something's always wrong. Somebody's going to have to manually come and correct it. It makes the automatic process really difficult. So can we get this number down? The answer is yes. The easiest way is what we just saw. I mentioned the threshold. If you have the threshold at 0.95, you have 5 internal anomalies and 21 false positives. Okay, if you put it at 0.99999, so you're really telling it you have to be almost certain about your anomalies. Nicely enough, the intended anomalies still 5, haven't lost out on that, and your false positives drop down to 6. Okay, this is great. Also, little disclaimer, this is in the context of my experiment. If you do it on yours with different data, who knows what the results will be. But this is like a good example of what things will look like. Okay, great. Increasing the threshold, that works kind of as expected. Now, some of you might be saying, throw some training data at it, so it could do even better. Surprisingly, it didn't actually. So what happened is I gave it all of 2017 data to try and to train the model on. And then I asked it, okay, sorry, all of 2016 data. And then I gave it a month in 2017, put some anomalies in there and asked it, what are the anomalies? It actually gave me more false positives, which wasn't great. But when you think of it, if you're giving it a whole bunch of training data, and this is not controlling anything else, you do have overfitting that comes in. So overfitting means that it's very much trained on 2016 data. 2017 will naturally be a bit different. And so it wasn't actually helpful in that sense. But like I mentioned, we haven't tuned the model. We've just thrown more data at it. So the third thing you can do is you can tune your model. So with the ARIMA model that I just used, there are three things. Sorry, this looks really complicated, might bring back some traumas from uni if any of you had to use this. But there are three things that you can change when tuning. So the ARIMA model is a combination of autoregressive and moving average part models. So you have three values. P is the order of the autoregressive, Q is the order of the moving average, and D is the degree of differencing. If you don't know what those are, again, I'll show you the article so you can find out a bit more about that. So you don't need to understand everything that's going on here. Just know that the more purple a point is, the better, because it has less false positives. And what you find out is that the purple really likes to live around here. So that means the P term is basically 0, the D term is 0 as well, and you just have the Q term. So what you find is that in the case of energy generation, the model you have is mostly a moving average model, because that's why you kind of cut out the other two terms and you've really focused on this third part here. Okay, so we tuned the model. Does that make a difference, not false positives? Yes, it does. We drop down to a single false positive on the same data that we saw right at the start. So just to summarize a bit what we've seen, OpenAI is good with anything to do with text. It can find anomalies quite rapidly. It doesn't need too much data to train on. On the other hand, BigQuery is really good with numerics, but it struggles with false positives. So the best way to reduce those false positives is really to try and tune the model, get it to fit your case much more accurately than just the generic automatic generation of ARIMA. And that's it. So I did mention that I wrote some articles with all the code in there, so you can actually do this yourself. So I have published them on Twitter and LinkedIn. Twitter tends to be more active because I like doing random investigations and then sharing them on that. So if you're curious about following those random investigations, I'd recommend following me there. Otherwise, I'll post the articles on LinkedIn as well. And that's it. And a little bonus before I'll come back to the slide. I did try something other than OpenAI. I tried Mistral. It's not good. That's all I've got to say. It's catching up, but it's not good. I'd actually have.